So we've looked at a broad brush overview of wave phenomena. We're now going to look specifically at reflection and also transmission when we're dealing with strings and ropes. Now this is a little bit of a sort of an intro that will allow us to sort of delve into a couple of other phenomena that are a little bit more useful. So this in and of itself is more about just basically understanding the foundational elements. So we're now looking at a situation whenever a wave encounters the boundary between two media. We're always going to see this idea of reflection and transmission. So we already know what reflection is. It's the bouncing back of a wave. Transmission is then just the transferring or the movement of the energy into the new medium. And so we'll see both of those occurring whenever we've got the boundary between two media. What happens with that transmission and reflection depends on the two media themselves. So we're not necessarily going to quantify this as a relationship as such, just going to do it sort of qualitatively so that we've got an understanding of what's happening with the transmission and the reflection of these. And the amount that's going to be reflected and the amount that's going to be transmitted will depend on the properties of the two media themselves. Now, rather than talk about, write lots of notes about what's going to happen with reflection and transmission, I'm just going to have a look at some examples. So the first one we're going to have a look at is if we had a light rope connected to a heavy rope. So this scenario, you're not really going to come across it all that regularly, say two ropes of different masses joined together, but it helps, as I said, to sort of describe some of the phenomena that we'll see, or some of the basics that will allow us to link into a couple of other key ideas or key concepts. So these two ropes, you can see the representation there, the light one being very thin, the heavy one being much thicker. To begin with, we need to identify a few properties about this scenario. So we've got our incident pulse, so we'll just call it pulse, being just a single crest in this case, and a couple of the properties that are important to note here are things like the speed of the wave, so v1, the wavelength, or the pulse width, I suppose we should really call it. In this case we'll call it lambda 1, and the amplitude of that pulse being a1. Now when we have the after scenario, what we're going to see is that some of that energy has been transmitted. So it'll look something like, well, it's a little bit uneven. Some of it will be transmitted. You'll notice that the amplitude there is fairly small, and some of it will be reflected, and in this particular case the reflected pulse is going to look like that. So there's the reflected, and on the right is the transmitted. And we need to identify again all of those quantities. So we've got the amplitude A2, we've got the wave speed V2, and we have the pulse width again, so it'll be this length here will be lambda 2, and then likewise over here we've got our pulse width, I'll call that one lambda 3, speed V3, and the amplitude, so we'll look at sort of the center of the rope, how much that's moved, and so that would be our amplitude A3. Now in this case, when we're looking at the quantities there, because the energy that we start with is some's going to be transmitted, some's going to be reflected, we're going to see that the amplitude there, A3, will be less than the amplitude A1. Likewise over here, the amplitude A2 is going to be less than the original amplitude A1. Now, because we've got a heavier rope, it's going to be harder to move it, and as a result it means that the speed of the wave, so V3, is going to be less than the speed of the wave in the lighter rope. With V2, because it's still in that lighter rope, that's going to be the same as the speed V1. Notice I'm talking speed here, not velocity, so just looking at how fast the waves are moving. The other thing that is important to note here as well is that if there's a change in speed, we're also going to see a change in wavelength. Now, the frequency with which the particles moving up and down will stay the same, but the wavelength will therefore change, and so as a result our wavelength lambda 3 will be less than lambda 1. But over here, because the speed is still the same, lambda 2 is going to be the same as lambda 1. Last thing to note then is that this pulse here is inverted. Now the reason why it's inverted, we can refer back to Newton's third law here. So as that pulse reaches the boundary, so the lighter rope is trying to pull that rope up, pull the heavier rope up. But the heavier rope, being heavier, is going to exert an equal and opposite force on the lighter rope that pulls it down. And now because of inertia, the heavier rope's not going to move as much as the lighter rope, and so this force down causes the reflected pulse to then be inverted. So there's a lighter rope to a heavier rope. Let's now reverse that and look at a heavier rope to a lighter rope. And you'll see basically here that most of that is kind of just reversed. So heavier to lighter rope, we're going to see first of all that we'll have this waveform being transmitted along the heavy rope, and then we'll go into our lighter rope on the right hand side. So I'll just note again, that's the heavy rope, that's the light rope. Again, we've got our velocity V1, sorry, our speed V1. We've got our wavelength or pulse width here, lambda 1, and we've got our amplitude would be A1. Now in this case, when we see the reflection and the transmission, what we'll notice here is that we get sort of the, as I said, the opposite sort of thing occurring, with a couple of key differences. So there's our reflected pulse, and you'll notice it's the same way that the incident pulse was. So we'll call that again V2, this is V3. The wavelength here will be lambda 2, or the pulse width will be lambda 2. Pulse width over here is lambda 3. And the amplitude here will be A2, and over here is A3. Now in this situation, if we sort of compare the reflected and incident pulses, we have the same sort of thing as before. That amplitude is going to be less than what it started at because some of the energy is being transmitted. The wave speed, V2, is going to be equal to V1. It's the same rope, so the speed doesn't change, and that likewise means that the wavelength lambda 2 is going to be equal to lambda 1. On the right hand side, I'm not going to make a direct comparison with the amplitudes. It's a little bit hard to identify what the amplitude will be here, considering that it comes back to the inertia of the two ropes. So in some cases it is actually possible for the amplitude of the lighter rope to be greater than the heavier rope if it's significantly lighter, and so it's easier for that rope to move, and so the amplitude can increase. So I won't make a direct comment about that. What we can also look at though is that the speed V3 is greater than V1, and that means that the wavelength or the pulse width lambda 3 will be greater than lambda 1. You'll notice here that the wave is upright, and the reason why that wave is upright is due to inertia. So because the lighter rope can easily move up, then it means that there's no sort of significant downwards force due to Newton's third law that will cause that heavy rope to be inverted. So there's the initial sort of ideas behind reflection and transmission. Why don't I just quickly look at the sort of the extreme scenarios? And what I mean by extreme scenarios is, instead of thinking about just ropes, a heavier and lighter rope, we're going to take it to the extent of looking at what happens where if we've got a rope that's not just going to a heavy rope, but it's now going to effectively an infinitely heavy rope, otherwise known as a fixed object. So imagine that that's a wall or a pole or something or other where the rope is attached to it at this point here. If we've got the rope connected to a fixed object, as we saw before, the pulse that we're going to get reflected will come back inverted. So that's the first thing to be aware of. And all the properties there are the same, so the speed's still the same, the wavelength, the amplitude. In this case, speaking of amplitude, most of the energy, and we're going to consider it that it's close enough to all of the energy, is going to be reflected. So because it's attached to a wall, there would be some sound and heat potentially being produced, but we're going to just sort of ignore that and treat it as being negligible, and say that most of it, close enough to all of it, will be reflected. And it will be inverted due to Newton's third law. So there's the extreme example of a rope attached to a fixed object. The other extreme example then is, so if we reverse the scenario that we were dealing with earlier, and if we look at going from a heavy rope to a lighter rope, that's basically the same as looking now at a free end. So this diagram here, think of it as being a rope that's attached to a ring. That ring's around a pole, and so this ring is free to move up and down with the rope that's attached to it. So if that's our incident wave, our reflected wave is going to look identical to that, but travelling back in the opposite direction. Now in this case, the reflected wave, is upright, because the free end is able to move as the wave approaches. So in being able to move, it means that it means that as the wave approaches, this ring can then move upwards, and so then as the wave has sort of hit that point and starts to reflect backwards, the ring then starts to move back down to its original position, and so the reflected pulse looks exactly the same on its way back. In this case, the same because it's sort of it's symmetrical. If it's not symmetrical, then you'd see that as it reflects back, the leading edge would still be in front. So if, for example, we had a wave that looked somewhat like that instead, so a bit of a triangular shape, then as it travels back, we'd expect to see that that leading edge of the triangle would still be in front. So there's the basics of reflection and transmission of waves on strings and ropes. We'll have a look at a few scenarios in class to identify what happens there, and then we'll take it a step further to see what happens as we've got more than just a single pulse, but a wave that's repeating as it travels in and back out again.